Thank you all for coming, and it's great to be here. Actually, I'm coming quite often because I like it so much. This presentation is about it's sort of a compilation of research efforts and also work with the government to try to understand what's the role of distributed generation and more generally distributed energy resources in the long-term planning in Chile. So we typically understand it as, or maybe let me say that again. 10 years ago, we used to understand it as solutions for particular remote communities in Chile. But now we're starting to sort of build a framework to understand it as one of the main solutions for the energy system in general. And particularly, Chile has very particular conditions that make it suitable for that. So first, let me just tell you about what UAI and the Center for Energy Transition is. So UAI is a private university in Chile. Nowadays, I would say it's the third largest engineering school in Santiago. It started as a business school, but about 30 years ago, it started the engineering school, and nowadays the engineering school is it's the biggest school in the university, the one that brings more students and also that manages more resources in terms of research projects. So the UAI decided to create centers, but not only for research. They said, okay, research is part of the job of the academic. So if you want to create a center, it has to have some impact in society. So our mandate is to maximize impact in society, and that means getting involved with companies and the government in almost all the projects that we develop. And so that's how Centra started 2 years ago. And we divide our activities in 4 multidisciplinary challenges. One of them is clean fuel. We have been doing quite a lot of work in terms of green hydrogen in Chile. Understanding not only the chemistry of it, but also how to implement it in the nationwide scale. The second one is sustainable and resilient energy supply. That has to do with models for planning networks that are more and more resilient against climate change. Sustainable industry 4.0, that's basically converting processes to use electricity and green fuels. And the last one, which is more related to this talk, I would say, is sustainable energy in cities and communities. So we have a pool of, I think this is a bit outdated. We are now more than 20 faculty members and many graduate students. Okay, so let me start with the motivation. Which are the advantages that we perceive from distributed energy resources? Third, let me tell you my view of what's the value of electricity supply, or how we perceive value in the electricity supply nowadays. In the past, there's no doubt about it. We used to talk about kilowatt hours and security. Those were the 2 main important things to build a network. To get the kilowatt hours, cheap kilowatt hours, so efficiency, and security. And that's pretty much in the structure of all the regulation in electricity systems in Chile and everywhere else. So we care about making it cheap and making it easy. The decision model for such an objective is very simple. It's to generate kilowatt hours at minimum cost, complying with certain security concepts. And you can formulate that as a centralized management or decision-making process. And that's consistent with the centralized regulation where either the government or the regulator has a lot of tools to manage the system, but it's mostly centralized. Okay. Then today we added a few more characteristics. So we also find value in cheap kilowatt hours, system security as well. Also low greenhouse gas emissions, that's becoming a value of electricity. Also low intervention of electricity, that's also starting to gain more value. And as a society, in most of the countries, I would say, we are in the process of incorporating these new values into the regulation, either as targets, either as carbon prices, you name it, right? And the decision model for this is to still generate kilowatt hours at minimum cost, complying with security constraints, and now we added a few extra constraints, like environmental standards. So large-scale infrastructure, destroying natural ecosystems, for example, large-scale hydropower plants, which are nowadays opposed by local communities. Nowadays, I would say in Chile is not feasible to see large-scale hydropower plants. The same thing happens with large HVDC or HVAC lines that take 10 years and lots of effort working with the community. Starting to get every time it's starting to get more expensive, more difficult, and more time consuming to build those.
Yeah, sorry for the interruption.
Go ahead.
Make it dynamic.
Sure. Yeah.
Because it wasn't kind of ready to that.
No, it's fine. Yeah.
Kilowatts today. Not only kilowatt hours, but kilowatts in terms of capacity.
Oh yeah. I was just trying to summarize the main concepts, but of course, power and energy are required. Yeah, you're right. So what should we expect from the future? And that's the question. But some people are trying to answer, some positions, some countries are trying to put new values into the what constitutes value in the energy supply. So in addition to kilowatt hour, kilowatts, low emissions, low intervention of ecosystems, system security, I put it into question just because it is not clear now whether we have to provide that at the centralized level or at the distributed level, because we could do both now. We could provide security at the distributed level. Local production, so some countries in Europe are starting also to see value in purchasing energy from local. Same way you buy milk and other resources from local community, energy as well, because energy can be produced locally. Self-generation, resilience against catastrophes. These are all questions, right? But these are all values that have been named in public policy in the world. So maybe in the future, we will have to add all these to our mechanism to build electricity systems or energy systems. So what's the decision model for this? I don't know. But I'm most certain that it's hardly consistent with the centralized management and so when you have to comply with so many different ways of perceiving value in the electricity supply, it's more difficult to come up with a centralized input, and you have to then resort to a decentralized way of deciding what to do and centralized ways of producing and investing in them. So, which are the advantages of decentralized energy supply solutions? First, in addition to trying to respond to all those values, right? Some of the advantages are modularity and adaptability. So those are great things about distributed generation, that you don't have to build large-scale infrastructure and convince communities to do it. Because if you want to supply your load, you can do it in your own rooftop, for example, or in the same area, and so on. So it's modular and it's adaptable. You can just build parts of it and start growing it in time. You don't have to build a large infrastructure all of a sudden. You can build it gradually. Second one is that some people say, so fosters local industry and new business model, because you have everything decentralized, you have many offers, demand is widespread, offer is widespread, so it's more likely that you end up with novel ways of supplying energy, either with new technologies or new business. The third one is resilience, and this is one of the main drivers of microgrids nowadays. So you can supply your load locally. Your community is going to be more resilient to climate disruption, for example, more frequent floods, any weather-related catastrophe. And this is, by the way, one of the main motivations of the development of microgrids in Chile. And some global trends that we observe that are consistent with what I just told you are, well, I'm sure I don't have to convince this room that microgrids are global trend, make sense, they have lots of advantages, and we are starting to see, maybe 10 years ago, we were talking about microgrids in pilot projects and in research in the universities, but nowadays countries, for example, Chile, are starting to build national plans for that. So targets, 10-year frameworks, and we are working on that nowadays. Also, local markets. So this is mostly in Europe. We are observing types of organizations similar to what you see in Uber or Airbnb, sort of sharing economics for energy. So there are platforms that allow you to buy and sell energy from local producers through a platform, and that way you can help finance energy projects near your area, or from specific producers that are have certain attributes. And demand response and demand response agreement. It has been going on for also more than a decade. We're observing companies that are aggregating demand and they are providing services to the main grid. For example, frequency regulation, emergency load shedding, and we see different ways of incentivizing consumers to participate in this centralized. Okay, so that was the sort of motivation to start with. The rest of the talk is divided in 3 parts, just because they correspond to 3 different research projects that we tackled in time. So part 1 is called estimating efficient levels of penetration of distributed generation. The results that I'm going to show you come from a study that we did with colleagues from the Institute of Complex Engineering Systems in Chile in 2020 for the Ministry of Energy. This was in the middle of the pandemic, so talks at that time were about how to incentivize local economy, creation of jobs in Chile, and we thought this might have been a good solution for that. In the end, it wasn't a good solution for creating jobs, but we built several new mathematical models to understand the efficient penetration of renewables. Distributed generation. It was good for my job, yeah. So we performed the study, and the objectives that we set, the more technical objectives, I would say, was the first one was to adapt existing long-term supply planning tools that were used by the Ministry of Energy in several regulatory processes. For example, transmission planning was performed with this model. Nationwide long-term energy planning process, which helps the definition of public policy, was also using this model. And this model didn't have any details on distributed generation. So it was very difficult for distributed generation to show up in public policy if the model didn't include it. And after we do that, just run the model and determine which was the efficient penetration levels for of DG. So the starting point was the NEWEN planning model, which is a planning model developed in the Catholic University of Chile, where I was before, like 2 years ago. With the group we had there, we took the switch model, which is a planning model developed at the UC Berkeley and LBNL, and we upgraded it with several new features, particularly higher level of detail in operational features. We included a relaxation of the unit commitment constraints that will work well in planning models. We also included a much higher detail in the hydro, which is very important in the case of Chile. So if you don't model the hydro system in Chile, you come up with solutions that are not implemented. So the model solves the efficient transmission and generation planning for 20 or 30 years horizon. You decide. As I mentioned, capable of capturing some short-term dynamics with high level of detail. And another interesting characteristic is that it uses representative data, not as opposed to load blocks, which don't have like interdependence in time. So this model is good for modeling intertemporal constraints such as unit commitment constraints, energy storage. Model all that, you need to have a representative. We had a model of the Chilean electricity system. This is only half of the country. We have a couple of thousand kilometers south of this point. So this is the northern end. This is Santiago here, and then the south. We use exactly the same model, the same number of loads, the same candidate units for generation, the same candidate lines that the Ministry of Energy was using for their process. Right? So this is a state-of-the-art planning model with very realistic model of the Chilean energy system. And also, I have to say that this model was also validated in research, in a research context. We have published, these are only a few, more than 5 publications related upgrades to this planning model.
This is to look at the how much the system can absorb distributed generation.
Not the limit, the efficient integration.
Yeah. Okay. So if you're looking at that, I suppose this will be at the low voltage level.
Right.
So are you capturing the low voltage system?
Yeah. So that's the upgrade that we had, and this is what we did.
But with a 20 node model.
No, that was the original model. But then when we opened each load zone with more nodes, represent medium voltage network, low voltage network.
So you're going down.
Yeah, we're going. So in order to address Kankar's question, what we did is each load zone, or these 20 or 23 load zones that the original model had, we opened into medium voltage network, which is connected with the high voltage transmission network through what we call zonal transmission system in Chile. And then this medium voltage node, which is fictitious, right? It's a conceptual. It's not that we can identify this node in the system. We just created it. It's connected with the low voltage distribution network through what we call a high voltage distribution network. The good thing is that we have regulatory processes that calculate how much this costs and how much this costs every 4 years. So we have to calculate this because we have to pay distribution companies what the network costs. So we make an exercise. So we have for the different nodes because we have different companies in different nodes and the conditions are different. So the cost of the network is different. And we do the same process for the zonal transmission. So we have a very good graph of how much it costs to develop this network and these networks in dollars per peak kilowatt peak. Right. So and in Chile we have 2 regulatory frameworks for distributed generation. One is called the PMGD, which are for medium to large facilities up to 9 megawatts. So these are mostly at the distribution level, but they are fairly large. Typically in the surroundings of urban areas, they cannot be in the middle of the city because land is too expensive. And we have another regime which is called net billing. It's basically for rooftop solar in the main urban areas, right? So we said, okay, we can install generation here, we can install generation here, and we can also install storage here and storage here. We didn't use storage here. We could have added, but we thought it wouldn't make much of a difference between here. Okay. So now with this, we can model the fact that we install generation here. We can save some money on distribution network and some money on zonal transmission network. We also accounted for the fact that the storage is next to the load, then the energy doesn't have to flow through here as well at any time. And we had very good, reasonable cost parameters for all these areas.
How do you deal with the parameters for those distribution grids?
You mean?
How deep they are, or your plan came up?
Oh, okay. So we assume that the existing network was good enough to supply the peak load, plus I think we estimate 15% margin. So beyond that, if you want to increase load beyond that, or generation upstream, beyond that, we have to invest. To invest, we have this cost parameter. Okay, so and then we build several case studies with the following approach. First, we assume that the penetration of distributed energy resources, because we're planning centrally. Yes, go ahead. No, it's fine.
Do you consider like specifically for technology or is it general?
So
I mean, wind, solar, things like that.
yeah, we consider. So good thing is that in Chile we have been thinking about this a lot of for a long time. So we know how much the potential of run-of-river hydro and wind is on these nodes, and we know how much the solar irradiance along the country for this node. So in this node, we don't consider wind because we don't think it's feasible for urban area. So here we can only install rooftop solar, and here we can install run-of-river hydro, wind, and solar. Those three. Yes, with very specific cost parameters that have been obtained by several studies in Chile specifically. So it's a very tailored model for the Chilean reality. Okay, so we assume that when you plan, or what we used to do before this model in Chile, we still do it. We haven't managed to convince the government to incorporate this into the planning process. It takes some time, right? But what we do now is to assume that distributed generation is going to grow by means of we model it as a consumer adoption model, right? The same way we would model adoption of electric vehicles. That's what they need for distributed generation. So it wasn't centrally planned, it was an the model for each year. So what we're going to do now is say, okay, what if we centrally plan? We're not going to centrally plan it. The government is not going to decide who installs PV. But just for the sake of the analysis, we said, okay, what if we centrally plan, which is the same we do with all generation, even though it's private. We centrally plan DG in our model. Okay, so it's going to be all centralized planning of generation at large scale and distributed. We also have to make an assumption, say, okay, we cannot just overflow well, we cannot just put as much distributed generation as we want in the distribution networks and just assume that it's going to cost nothing in terms of infrastructure. At some point, we're going to have to adapt infrastructure, make investments in distribution systems so that we can keep it. We didn't have a good number back then as to how much we can increase. So one of our colleagues, which was an expert on distribution network, said, well, the latest study that we run is that up to 30% peak load, you have absolutely no problems in distribution network. So say you have a feeder which is sized for 9 megawatts, that's sorry, 27 megawatts of load. So you can incorporate up to 9 megawatts of solar without having to make adjustments in infrastructure. So if we extrapolate that metric to the whole system in Chile, that adds up to 1.8 gigawatts of peak solar power that we can install in the low voltage distribution networks. That means segment that may be rooftop solar. So this was the best estimate we had at that time, but as I'm going to show you in the second part, it proved to be overly conservative. Now I'll show you more on that. We consider all several decarbonization plans that were being discussed back then, like whether we should phase out coal by 2040, 2030, 2035. There were several options that were being considered back then. We consider also following technological design. First, we assume that we just let the model run and decide how much distributed generation we should install. But then we run two case studies forcing penetration to be 50% and then forcing penetration to be 100% of the available, just to see how much it costs, right? Then we also assume that the decarbonization process, it means phasing out coal. That's what we mean with decarbonization of the electricity system. We tested scenarios of decarbonization by 2040 and decarbonization by 2030 to see if it makes a difference in terms of distributed generation. And also we tested a target of 100% renewable by 2040, which is not only phasing out coal, but also natural. And we ran several sensitivities on key parameters of cost, demand growth, and other sensitivities related to candidates for transmission expansion in Chile that was more of the discussion of that time in Chile. It's not that relevant for the results that I'm going to show you now. So these parameters, it's important to understand the results. We define what we call the net differential benefit, which is a difference between this parameter called CDT, which is the net present value of the operational and planning costs for the base case scenario, and then the CDG parameter, which is the net present value of the operational and planning costs of each corresponding scenario. So we have a base scenario that we are going to compare to several other sensitivities. So this delta DG for the base case scenario is zero, because CDT equal to CDG, both costs are the same. But then we might try different scenarios: low cost, low development cost, high development cost, low demand growth, forced 100% DG. Different scenarios are going to make that parameter. So, one thing I didn't mention is that we also try 14 DG to 0. So say no DG. What happens if we don't implement policy, or we have a regulatory structure that puts so many barriers on DG that we cannot develop it? How much it will cost to the Chilean economy? We can get it from this parameter. So in the base case, what we observe is that in the low voltage networks, that is neighborhoods, houses, mainly rooftop solar and distributed storage, in the base case, we reach 52% of the total hosting capacity. So we said the distribution feeders can take up to 30% of peak load, can take capacity, DG capacity up to 30% of the peak load. And when we run the model, the efficient solution was that we use 62% of that. But in reality, what we observe, if we observe Chile, like a very long country, we observe that from the north to Concepcion, which is the city south of Santiago, all the feeders were saturated. So all the feeders installed 100% of their hosting capacity. And then to the south, only a few of them installed, just because of the solar irradiance much higher in the north, right? And that's nearly 1.12 gigawatts of solar PV capacity in distributed generation. So this was an interesting result, because nowadays the capacity of net bidding projects in Chile is 150 megawatts. So it's less than 15% of the capacity that we should install in an efficient planning process.
So why is it taking off so late?
Why is it what?
Why is it so much shifted on time?
Here you mean, because why we have so much here and so little here?
There's a big demand growth.
Yeah, it's mangrove. Yeah, it's basically the mangrove. So here we have a lot of potential as well, but we have existing legacy assets, so that's why it doesn't make sense.
What is the rate of growth?
I think what we assumed here was about 7% per year. Load growth. Yeah. Almost doubles for the years. It's very coupled to the growth in mining, in the mining activity, actually in Chile. So if you see the growth in the mining industry compared to the growth in electricity consumption, they go head to head. We also observed that nearly 1 gigawatt of storage was installed in, yeah, yeah.
Wouldn't be 7% growth,
7%.
7% growth, annual growth.
That's the basic assumption that the government makes in their planning process. So I'm sure they run a study, I don't know the specifics of it.
So I'm just curious, that because,
Yeah, I think the main, as I was saying, the key drivers of that growth is the growth in mining. And then they also have mining industry. Mining industry is the main driver for demand growth. So we also, the model also installed nearly 1 gigawatt of 1 gigawatt of storage in low voltage networks. And we assume that all the storage we installed was 4-hour storage. So 1 gigawatt of storage means 1 gigawatt of power, 4 gigawatt hours of energy capacity.
Sorry, I just wondering with your planning process, are you also considering network constraints, network structure?
Yeah, absolutely, but only in sort of transport model, transport network model, you know, no DC load flow, yeah. Although the model can do it, it just takes so much time, and for the particular analysis that we were making, we didn't think it made much sense. Also, the network is just a line, so it wouldn't make much of a difference whether you use DC or not.
Simpler than the.
Yeah,
Without that.
exactly, yeah. So just assuming that these are hybrids.
Yeah, part of the reason I asked, because you were saying that you were saturating the investment we solar in northern climate.
Yeah.
So I guess that then would be whether you have like more those regions.
Yeah, you know, we might, but resolving voltage issue is so much cheaper than solving thermal issues, for example. Then we just assume that even if they show up, they're just gonna add maybe 0.5 or 1% of the cost in the end. You just need reactive power from the city. If you run out into thermal constraints, which is what we model, then that's the real issue. Yeah.
Can you repeat the question? When you answer questions for people?
Oh, yeah, okay, we'll do. Okay, so also in the base case, we observed that in high voltage distribution network, remember these were projects up to 9 megawatts of capacity installed near the cities, but not inside the cities, also not in large high voltage transmission networks. We observed that the model invested 5 gigawatts of DG by 2040, and also 2.7 gigawatts of storage in those networks. We, as I mentioned, we observed that the constraint of maximum penetration of these in low voltage networks was binding in most of the country. Concepcion to the north, all the low voltage networks were saturated. They reached the maximum capacity that we set. And remember, I mentioned that was a sort of rule of thumb that we applied. We weren't that sure that that was a reasonable limit. We also observed that efficient integration of DG in low voltage and high voltage, they add up to 6.22 gigawatts of capacity by 2040, and that represented in the model 40% of all the new generation capacity that was installed in that 20-year horizon. So from 2020 to 2040, 40% of all the new generation was distributed. So this was a very relevant resource. So that you make sense of the number in terms of the size and what it means for Chile. 6.22 gigawatts, 40% of all the generation that the model installed between 2020 and 2040. So very, very significant. It also installed a lot of storage, not only low voltage and high voltage distribution, but also in the bulk power system. If we add up all of them, it installed nearly 12 gigawatts of storage capacity, which means 48 gigawatt hours of storage.
Thanks, yeah. I was wondering, does Chile not have a considerable amount of natural gas? Because in countries like North America, that can help be cheaper than some of those alternatives.
Yeah. Yeah, so the question is whether, I'm gonna repeat the question. The question is whether Chile has a good potential of gas resources. And the answer is no, we have almost nothing. We have Argentina right next to us, which has a lot, but in the past, Chile has had troubles getting that gas, even though there were international treaties for that. Back in the late 90s, there was an issue and the pipelines were closed towards it. So in terms of security, it's not considered secure for Chile to depend so much on natural gas. But we do have a lot of gas in the electricity system now. The thing is that when we project towards the future, we try to just make it decrease down to zero in the 2040. Yeah.
The reason for this, okay, my question is, are you modeling frequency calculation in some way or not?
Yeah, the
The
question
question is not why so much.
yeah, so the question is whether we model frequency regulation. In the model, the answer is just that the reserve requirement in the operational model. The reason why we have so much storage is because, well, we have a PV, right? We install cheap photovoltaic solar in the north, means that we have to store supply at night, and also as an alternative to transmission capacity. Okay, but here's one interesting thing about the result right away, is that if we have what I mentioned, nearly 5 gigawatts, that is 20 gigawatt hours of distributed storage, then we might need to revise the limit of 30% of capacity limit of DG in distribution feeders, because with the storage we can do load leveling, we can do energy arbitrage. That means that even if we have 10 gigawatts of peak solar, we can distribute that along the day, and it will end up being 5 or 3 or 4, right? So that's one thing we realized with the result, that there is so much potential for storage that we need to revise the limits of DG penetration in distributed. Also, we ran some sensitivities, seeing if there was a difference in the total CO2 emissions due to distributed generation. We didn't observe a relevant difference because the model was simply replacing DG photovoltaic by bulk power system photovoltaic. So that was training.
My question would be is, why the need to put a limit? Why not just put a limit of kilowatts on the transmission system, medium voltage, low voltage? So you see that from you don't do this kind of stuff.
Right, so we did both. We did both. We did so we did impose a limit on the transmission between low voltage and medium voltage and the medium to bulk power system. The thing is that we had a cost parameter for that. So we also included a decision that would be to expand that capacity and install more transmission or distribution. What we didn't have was a parameter to say, okay, how much it costs to install DG all over the distribution grids when it gets saturated. So we know how much it costs from low voltage to medium voltage, but inside low voltage, to make it all work inside the low voltage network, we didn't have it. We didn't have a parameter. That's why we assumed the 30% on that node. How am I doing in time? Well, this is just part one, but I can, how much time do I have?
15 minutes.
Okay. What if we leave the questions to the end, but let's go with this one and then.
Okay, I just wanted to ask why it's 4 hour energy storage, why it's good 4 hours?
Oh, no particular. Yeah, so the question is, why did we use 4 hour energy storage? That's just the standard that you observe when you go and try to find prices and price projections to the future. typically you see 4 hours storage. The thing is that it doesn't really matter, because if you install twice as much, then you have a 4-hour storage, and the model will recognize that. We're not limiting energy shifting within 4 hours. Okay, so that was the first part, and then we said, these results are interesting, but it seems that this condition that we applied, the 30% peak load as the limit for DG low voltage networks, is binding all over the country. So we might have to look into that assumption further. And that's why we, last year, we created the Industrial Research Chair Program, which was funded by ASOL. ASOL is the local association of developers of distributed generation. And they wanted us to understand, first develop tools to understand how much we can actually integrate into the Chilean distribution network without having to invest significantly on upgrading it. Right? So basically they were saying, okay, how much that 30% limit really is? Is it 30%, 45, 40, 50? Okay, so the project had a broader scope. Actually, they wanted to also observe several regulatory barriers that we can observe in Chile. But in particular, we wanted to, as a tool to answer all the questions that people had, we wanted to develop a computational platform that would help us to automate the analysis of hosting capacity in distribution feeders in Chile. Right. The information for that was all over the place, different sources. You could get this database from a system, and you try to draw a single line diagram. There would be islands all over the place. So information was incomplete. Several sources of information. So we had to build a routine that would take all that information, filter errors out, build the network, and then send you a report with a lot of flags saying, look at this, look at that, because there might be an error. So we did that with the support from local distribution companies as well, and we managed to model a large area of distribution in the south of Chile using this. So basically, the platform that we developed is a platform that takes different databases of information, technical information about the distribution network, that length of the feeders, electrical parameters, thermal limits, so on and so forth. So we created a tool that performed an automated network modeling. We also developed another tool that made a clustering of load profiles so that we can run then Monte Carlo scenarios later, picking scenarios from different classes or clusters. We also created an estimation of hosting capacity, a tool for the estimation of hosting capacity, which is based on a very well-known software that's called OpenDSS for distribution network analysis. And we also created some visualization tools. We're still working on this. The ones on yellow on the background are already done. We are still working on the other tools for the second year. Right, so we work with SAESA, which is the local distribution company in the south of Chile. They facilitated all the data from their networks. So we were able to replicate with operational results for nearly 50 distribution feeders that composed all the distribution network that they own. Sorry, there are some information in Spanish here, but as I mentioned, we created these different clusters of loads. The idea here was to say, okay, we don't have the specific load profiles of all the distribution feeders in the country. We have a few with smart meters, which are not widespread in Chile yet, but we have a few database information from smart meters. So we say, okay, let's classify our load data in 5 classes. These are, in general, well, you cannot make much sense out of this, but this is more of a lot of residential profile here. We have a commercial profile, sort of mix of residential and industrial here, an industrial profile right here, and another sort of mix of commercial and residential profile. So the reason why we build these clusters is so that when we try to analyze different feeders for which we don't have load profiles, but we do have information about the users on that network, meaning how many residential consumers we have, how many commercial, how many industrial, we can get data from these clusters. 40% of the load is residential. So we get from here and from here, 40% of the load profiles. 20% is industrial, and we get it from here. So that's why we made this specification. And then we build this simulation model, which is basically running Monte Carlo analysis with different assumptions of load profiles, several scenarios, and then for different levels of penetration of distributed generation, we'll observe relevant results, which are basically low voltage level and thermal limits.
This study is for a specific distribution network.
The model is built for specific feeders. Feeders, which then we apply to a whole distribution network, which then used to extrapolate to the whole country. So there's a couple of steps extra on that. So this is the kind of result that the model offers. So we take the basic load profile. So we know the measurement of the load profile in the substation. We don't have information downstream. So we start feeding load profiles to the feeder until we match the measurement in the substation. And then we started integrating distributed generation and observing what happened. And what we observed is, for example, these are the results for voltage. Right? So at some point, if you start integrating more and more photovoltaic, you will have a high voltage during the day, peak high voltage when PV generation is at the peak and load is low, then you will have high voltage at the end of the feeder. And that would be the technical limit violation that will limit the hosting capacity of the. We also observe other limits, for example, thermal limits of secondary transformers, which are transformers downstream of the main distribution substation. What we observe is that you can start adding penetration of photovoltaic, and at some point you will hit over voltage limits, which is the yellow line. So after 10%, you start hitting voltage limits. After 30%, you start hitting transformer thermal limits, and then eventually you will hit conductor thermal limits, but that's very rare. So here, just to mention, here 10% means 10% of consumers having photovoltaic systems. It doesn't mean 10% of the peak load. It actually, 10% is actually nearly 60% of the peak load. So what we did next, so now we have a tool that helps us understand how much the hosting capacity of one particular feeder. And we have 20 feeders from this distribution company. But we have the information of all the feeders in the country, not to run power flow analysis, but good enough to make clustering of distribution feeders and associate a centroid within the feeders that we do have information. Okay? So the blue ones here are all the feeders in the country, organized by length in kilometers and peak demand. So we use a very basic technique to say, okay, this feeder for which we have detailed electric model information is going to represent all the feeders in the surrounding. So to each of the feeders that we did have detailed models, we associated a few feeders at the national level. And then we use that to extrapolate how much hosting capacity of the whole country. And what we observe is that if we only care about voltage limits, then we can integrate up to 12 gigawatts of peak solar generation. That's almost 7 times what we assumed in the previous part, where the peak was at most 1.8 gigawatts. That's what we tolerated. If we also consider secondary transformer thermal limits, then the limit goes down to 6.55 gigawatts. So what's binding first in Chile is the limits of the secondary transformer.
But that's not the plug,
Where?
previous plug.
This one?
First was voltage, then transport. No.
Oh, yeah, but this is for one particular feeder. This is for one particular feeder. This is for all the feeders in the connection. Okay, but the secondary transformer is those that you see on the street, right? It's not in the substation, it's downstream the substation. So my perception, we didn't run the study again, but my impression is that that's not what's going to limit DG penetration. You just change the transformer. It's not going to add an significant extra cost, right? So I think this limit is not hard to overcome, rather cheap, right? So if we look at this figure, 12 gigawatts means that without implementing mitigation measures that are going to cost us a lot, so just changing secondary transformers, the limit that we used in the previous part can increase nearly 7 times. So the results that we obtained before are way over conservative. Okay, so just this is just to open the discussion. These are some ideas that after this result, some ideas that keep me awake at night. First, it seems to me that if after these results, at least in Chile, it seems to me that the electricity system has to be built all over again today with the current technology. So just destroy all electricity systems, have to start all over again. We would not require the establishment of a centralized planning process of any kind. Transmission, long-term energy tenders would not be necessary, which is just good. This could just be deployed in a completely decentralized manner, like everybody just installs panels, batteries, a few distribution lines on a community, and that would be it. Okay, I'm sure this is going to create reactions. So
Those are not used.
no, these are not my results. No, these are just ideas. Oh, you mean my results contradict this? Well, the thing is that we started from legacy assets. We didn't run the study from zero, from scratch.
But you have to be that.
Yeah, that's one thing. So if it had to be built from scratch, so that's a something. If we had to build it from scratch, yeah. Forget about forget about that part of agreeing and a new society with electricity first, right? But okay. Second, so decentralized what?
The decentralized other system would be a huge increase.
Yeah, I agree. I agree. This is not a real reasonable question. Like we're not asking ourselves this, right? But what does it mean for the current design of electricity market? So should we change them completely, favor this solution? Does it make sense to do that with all the legacy infrastructure that we have? To try to achieve that goal that we know maybe that would be the efficient solution of a fictitious optimization problem that we run now. But does it make sense to point in that direction?
My question is a little bit behind.
Yeah.
Your second work, where you followed a bottom-up approach.
Yeah.
Why didn't you do the same thing for the first one?
Oh, the thing is that we did the other one first. That's the only reason. But now we are rerunning the results with this.
I think this approach would be more suited for that purpose.
Yeah, definitely. We can just rerun the results, the other one, upgrading the capacity limits of low voltage networks. That's what we're going to do now. But it takes some time because we also want to add some constraints related to reliability. So see how much reliability can we get from low voltage networks with DG and storage. That takes some more time. So should we design a trajectory from the current market design to a fully decentralized market? That's something to wonder. Or are we trapped in a local minimum? So just solve this algorithm with of course, non-convex, and we ended up here, right? Where as if we start again, we would end up somewhere here, right? But the cost of transitioning there doesn't make sense to spend it.
Excuse me.
Yeah.
Have you made any studies, what would be the impact to the cost of investment?
So this is the centralized efficient solution. So market design aside, this should be the cheapest solution for the consumer. Now you have to bring the market layer and anything that can happen after that. So I don't know, because I don't know how to implement this, because we have to redesign the market. But from a centralized perspective, this would be the cheapest solution. So these are other ideas more down to the earth, I guess, so this only keep me awake during the day. So the large penetration of distributed, huh?
Now you must, now you must.
Yeah. So the large penetration of distributed storage that we observed in the case study of the first part can unchain a much higher capacity of distribution networks and also can in fact higher resiliency and reliability. And that goes to your question, Pankaj, that we have to redo the first study again, considering both higher limits of low voltage networks, but also the contribution of storage to resilience and reliability, and we have to find a constraint that values that inside the model, either as a constraint or in the objective function. The results suggest that the massive deployment of DRs in Chile can happen by private initiative, because this is a centralized planning model. If we design the market appropriately, then this can happen by private initiative. We don't need to put incentives. Should happen naturally, but it's not happening. Why it's not happening? Well, there I have a slide. There are some specific barriers that we have identified that are not allowing this efficient solution to be materialized. First, the structural barriers. And I think the most important one is that the overall electricity market design is based on the construction and operation of company-owned large-scale generation and transmission infrastructure. This brings together a wide variety of barriers in general, and we could term this discrimination by emission. So all the decisions we make are, okay, where do we build the next large-scale transmission line? Where do we build the next large-scale generation? Those are the questions that the regulator is not asking where do we build or how do we build DG. So by omitting DG from the public policy discussion, we are sort of not allowing them to flourish. As an example of the above, when we plan the zonal transmission, this transmission system between the power system and the distribution system, we only consider that new investments are going to be triggered by demand. Okay. When somebody comes and say, hey, but I want to install the medium-sized PV facility here. Oh no, we're not going to consider that into our planning. Just we're going to trigger new infrastructure because of demand growth. So, we also do the same in distribution network. Distribution network is planned for demand growth, and it's also paid for due to demand growth. So when we calculate how much we have to pay the distribution company, we calculate how much infrastructure we need to supply the load. Not how much infrastructure we need to supply the load and allow energy transactions in the network. And also, well, some other barriers, I would say these are second or third generation barriers, have to do with limited access to some markets for distribution. There are also issues related to information transparency, education and financing. So DG developers have trouble getting funding from banks because there's no culture in banks, there's no process, procedures to analyze the investment. And also because they don't have access to many large markets. That's why it's difficult to estimate how much revenue they're going to get. Okay, so yeah, I think the last one I already summarized. So that was pretty much it. Thank you.